Yesterday we introduced this idea of heavenly motion, the motion of planets, for the most part, around the sun. Although we can also apply this to the motion of asteroids around the sun, or the motion of satellites around the Earth, for that matter. We zoomed way back in time, about 2,500 years to about 500 years before the birth of Christ. We talked about a guy named Aristotle, who everyone's heard of before. Aristotle said a lot of things. One of the ideas that he put forth was this geocentric theory of the universe. Geo means what? You guys remember from yesterday? Geo means Earth. So the Earth-centered theory of the universe. Everything, all things in space, including the sun, revolve around the Earth. All the planets, all the stars, the sun, they all revolve around the Earth. And we said yesterday that doesn't seem so far-fetched if you take a step back from it for a second. When we look up in the sky, we see the sun in one spot at one time of the day. We see the sun somewhere else at another time of the day, kind of like we see the moon in one place and then another place. It only makes sense that the sun revolves around the Earth, but it doesn't. Okay, we know now, of course, that the Earth revolves around the sun. It just appears to us that it goes the other way around. Okay, look back at this and say, how could anybody be so ignorant, literally in the true sense of the word, to not know that the Earth revolves around the sun? Well, we wouldn't know any different unless somebody told you any different. And I probably wouldn't know any different unless somebody told me different as well. Okay, the geocentric theory, the Earth is the center of the universe. Everything revolves around the Earth, including the sun and all the stars and planets. And then we fast forward a couple thousand years to Copernicus. Okay, everybody's heard of Copernicus, the heliocentric theory. Might not know what Copernicus said, but everybody's heard of him. Helio means what? Sun. The sun-centered theory. All the planets, including the Earth, revolve around the sun. So here it's been almost 500 years now that we've known that the Earth revolves around the sun. We haven't known for 500 years how it revolves around the sun or why it revolves around the sun, but we've known for about 500 years that it does. Okay, the heliocentric theory. The Earth revolves around the sun. Fast forward 40, 50 years, Tycho Brahe. He was the pee guy. Remember the story about Tycho Brahe? He was the guy that was at the dinner party, didn't want to be rude to get up and go pee, so he held his pee. 12 days later, he died of a burst bladder. Don't hold your pee. Tycho Brahe, along with his assistant Johann Kepler, made some observations of the planets and the stars, and he measured some angles and measured some times and measured some distances and so on and so on and so on. Didn't do a whole lot with it, but took a lot of measurements. His assistant, Johann Kepler, after Tycho Brahe died, used that data that him and his boss, Kepler and his boss, Tycho Brahe, took, and created 3 laws that describe how the planets move around the sun. 1543, Copernicus said the planets move around the sun. Okay, the late 15th century, or late 16th century, I should say, Johann Kepler said, here's how they move around the sun. They don't just move around the sun, they move around the sun in a very particular orbit, an elliptical orbit. We don't have 2 suns here, right? We've got 1 sun. The sun is at a particular spot. Now the Earth will revolve around the sun in an elliptical orbit such that the sun is at one of the focal points of that ellipse. So in other words, the sun is at a particular spot. The Earth revolves around the sun like this, so that the sun is at the left focal point, or the Earth revolves around the sun like this, so the sun is at the right focal point. Okay, the sun isn't moving back and forth between one focal point and the other. The ellipse, in fact, isn't moving back and forth, so that the sun is at one focal point or the other. All we're saying here is that all of the planets, including the Earth, will revolve around the sun like this. Okay, and the orbit is going to be such that the sun is either in position 1 or in position 2. Make sense? The law of elliptical orbits, the Earth and all other planets revolve around the sun such that the sun is at one of the 2 focal points of that ellipse. Well, then we took a look at the second law, second one of Kepler's laws, and this was probably the toughest of the 3, I'd say. The law of equal areas. Here's the sun. Okay, the sun's going to be red now. Really hot. Here's the Earth. Let's make the Earth green because we want to be green. There's a line that joins the sun to the Earth. Now, it's an imaginary line. we're going to pretend there's a little string that joins the sun to the Earth. There's not really, of course. Okay, we're just going to pretend that. Let's fast forward a little bit later in time. Let's fast forward a week, 2 weeks. It doesn't matter. Okay, a month, 2 months. It doesn't make any difference. Let's fast forward a time that we call T1, whatever that time is. Now, the planet, the Earth or whatever planet it is going to be in a different position that amount of time later. Okay, it's going to be in that position. Let's fast forward another 6 months. The Earth is going to be over here. Let's say it's in position 3 now. Now let's fast forward a little bit more time that we'll call T2. The Earth and whatever planet it is now at position 4. If T1 equals T2, in other words, if this 1 week stretch or this 2 week stretch is the same time period as this 1 week stretch or 2 week stretch or whatever the time was, if T1 is equal to T2, then A1 will equal A2. The area that's swept out by the line that joins the sun to the Earth is going to be the same. Now, it doesn't look like the same area. Somebody yesterday asked me about this during scheduled help. How can that be the same area? This one's so skinny, this one's so fat. If this one is short and fat, this one is long and skinny. I can't calculate the area of that. I don't know how to do that. I don't know how to calculate the area of that partial ellipse there. There is a way mathematically to do it. I just don't know the mathematics of doing that. Okay, but you can see just kind of anecdotally, you observe it, say, okay, look, it's possible that this area is the same as this area. Okay, this one's a lot narrower, but it's a lot shorter, but it's fatter, right? This one's a lot longer, but it's skinnier. So it's entirely possible that those two areas are the same. If T1 equals T2, then those two areas are going to be the same. In other words, put this in words, a line that joins the sun to a planet sweeps out equal areas in equal time intervals. Okay. That third law, the last one that we talked about yesterday, the law of periods. If you remember, this one said that the square of the period of revolution of a planet around the sun divided by the radius of revolution cubed is equal to a constant. That constant's called Kepler's constant. Kepler's constant is the same for the object that's being revolved around, no matter what's revolving around it. So for instance, if I want to find Kepler's constant for the sun, I can use the period of revolution of the Earth and the radius of revolution of the Earth. Or I could use the period of revolution of Mars and the radius of revolution of Mars. These two numbers would be exactly the same, regardless of whether I use data for Earth or whether I use data for Mars. Okay, that's really, really practical for astronomers. Look, if you know Kepler's constant for the sun because you know information about the Earth, then that will allow us to get information about Mars or information about something else that's revolving around the sun. Now, having said that, Kepler's constant for the Earth is not the same as Kepler's constant for the sun. Okay, we have to use data about something that's revolving around the Earth. Maybe Kepler's constant for the Earth might be t squared over r cubed for the moon. Or Kepler's constant for the Earth might be t squared over r cubed for the International Space Station. So K is constant for a particular object being revolved around, the sun in this case, regardless of what data we use. Okay, it doesn't matter what's revolving around it, K is going to be the same for that object. Okay, but if we go to a different object, here it's the Earth being revolved around, Kepler's constant is going to be a different value. Does that make some sense? The law of periods, technically in words, says the square of the period of revolution of an object around the sun is equal, or of an object around another object, is proportional to the cube of the average radius of revolution of that object. Again, those words don't make a whole lot of sense to us. I hope that the mathematical explanation makes a little bit more sense to us. Travis? Yeah. Good? And finally, we talked a little bit about gravity yesterday and how gravity happens. Copernicus said the Earth revolves around the sun. Didn't say how, didn't say why. Kepler said this is how the Earth revolves around the sun. Goes in an elliptical orbit. Okay, the sun's at one of the focal points. The law of equal areas, the law of periods. This is how the Earth revolves around the sun. But he still didn't know why it revolved around the sun. We didn't know until 1687 when Isaac Newton comes along. The apple, the proverbial apple, falls on Isaac Newton's head. Okay, we didn't know until that time that it's gravity that causes all this to happen. We did a silly little demo yesterday where we said, have a look at your neighbor. Who wasn't here yesterday? Who was in band yesterday? Okay. Just a few of you. We did a silly little demo yesterday. Said, pick a partner. Okay, pick a partner. Those of you who were in band yesterday, pick a partner right now. Pick a partner that was in band. As other people giggle. Don't giggle, you guys. Get your partner? Okay. Okay. Look at your partner in the eyes. Repeat after me. Oh, look at your partner in your eyes. Repeat after me. I. You don't need to say it again. Sorry. Once is good. I am attracted to you. Oh, yeah, that was a little awkward actually. That was probably the most awkward one we've ever had actually. Yes. Sorry about that, guys. I should have warned you before that one. Yeah, I've never done that with twins before actually. Why? I mean, it's true, right? In the end, it's true. Everybody is attracted to everybody else, but not in the way that the joke is, right? In the end, everybody is attracted to everybody else because of gravity. Any two objects with mass exert a gravitational force on each other. Now, the gravitational force that you exerted on your partner just now, when you said you were attracted to him or her, is really, really, really small. Why? Why is that force of gravity so small? Yeah. You guys all have a very, very, very small mass in the grand scheme of things. Okay? The force of gravity of you and the Earth, between you and the Earth, is much, much bigger. You don't weigh anymore, but the Earth does. The bigger the mass, the bigger the gravitational force between the two objects. Now, here's a question for you. Why is it that if the force of gravity between you and the Earth, it's the same force acting on you as acts on the Earth, why is it that you fall towards the Earth and the Earth doesn't rise up towards you? It's the same force. Shouldn't the Earth be affected just as much as you? Well, essentially, yeah. It is affected. It does experience the same force, but we know by Newton's second law, A is equal to F over m. If m is really, really big, then the acceleration will be really, really small. In other words, is the Earth pulled up towards you? Yes. But it's pulled up towards you at such a tiny, tiny, tiny rate that it's not even measurable because its mass is so big. Make sense? All right. There is a force of gravity equation beyond the one that we've already learned. Okay, we said before F is equal to m times g, F is equal to m times 9.81. That's still perfectly valid. The only problem is we don't always know what g is anymore. We've assumed until this point that g is 9.81 meters per second squared, and on the surface of the Earth, that works really well. Although it does change a little bit. Sometimes it's 9.79, sometimes it's 9.82. Depends on where you are. Okay, people in the oil industry will measure slight differences in gravitational field, in the acceleration due to gravity, and that'll tell them different densities of the Earth. And that'll tell them maybe where oil is located because of different densities. Okay. Gravitational field, or G, a value that we consider to be 9.81, does change a little bit, but for the most part, it's 9.81. But what if you want to find the force of gravity on the moon? What if you want to find the force of gravity between the moon and the Earth, or between the moon and the sun? Well, we can't use 9.81 anymore. So what do we use? Well, we need another equation that's going to describe this force of gravity that doesn't depend on knowing what that value of g is, because we don't know what that value of g is everywhere in the universe. That equation goes like this. F, notice those absolute value signs again. Okay, in other words, it's a vector, but the equation is not going to tell us what the direction is. F is equal to g times m1 times m2 over r squared. You want to find the force of gravity between the sun and the earth. What's m1? Not the value of m1, but what does m1 represent, the sun or the earth? Doesn't matter. What's 1 times 2? What's 2 times 1? Doesn't matter what order you multiply two things in, right? Okay, whether you go the mass of the sun times the mass of the earth, or the mass of the earth times the mass of the sun, doesn't make any difference. Doesn't matter which one you make m1, which one you make m2. One of them is going to be the earth, one of them is going to be the sun in that case. What do you think r stands for? Be careful. When you're talking about the earth going around the sun, it would be the radius. But if you're talking about you and the partner you looked at and said, I'm attracted to you, okay, then it's the distance that separates them. Okay, unless you're dealing with a circle, and you are sometimes, okay, unless you're dealing with a circle, then r represents the distance that separates them, not the radius. Now, if you're dealing with a circle, then the distance that separates them is the radius. So let's say that this is, I'm going to label that, just so you don't get it mixed up with radius. It's the distance separating the objects. What units do you think you're going to be in for that? It's not chemistry class, so it's not grams. It's going to be kilograms, right? Oh, sorry. Well, it's not chemistry class. It's not going to be grams. It's also not going to be kilograms. The distance is going to be not kilometers. Let's go with those standard units, meters, right? Thank you, Travis. These masses are going to be kilograms, right? The mass of object 1, the mass of object 2. Yeah. What's what? Sorry? Let's finish this off and then ask that question as soon as I'm finished talking about this equation, okay? G is a constant. G is, I call it a fudge factor. Okay? Basically, Newton recognized that the force is related to m1 and m2 and r squared, but it's not equal to that. So we had to stick a number in front to make it equal, to make it always equal, and that number is G, gravitational constant. The gravitational constant, G, has a value of 6.67 times 10 to the minus 11 Newton meter squared per kilograms squared. Really odd units there, Newton meter squared per kilogram squared, but you don't have to remember those units because that constant's listed on your data sheet. Okay, always for a test or a quiz or whatever, you're going to see that number on your data sheet, including its units. Now, Travis asked a question just a second ago about is there a spot between the Earth and the Moon where the force of gravity is zero? We have this perception that gravity is zero in space. That's not true. Gravity is weak for the most part, not everywhere, but for the most part, gravity is very, very weak in space. And the reason for that is because we're far enough away from objects that produce gravity that there's not going to be much of an effect, a negligible effect oftentimes. But there are places where the gravitational force is zero. Now, if you go between the Earth and the Moon, okay, the Earth is pulling you one way, the Moon is pulling you another way. The Moon is lighter, so it's not pulling you as hard as the Earth is, right? That would mean that in order to experience no gravity at a spot between the Earth and the Moon, you would have to be closer to what? You'd have to be closer to the Moon. Good. In order for the Moon to cause the same force of gravity on you as the Earth, you need to be closer to it. So there would be a point between the Earth and the Moon where the force of gravity caused because of the two of those would be zero. but there would only be one point. Everywhere else, there is still gravity. It's just small because you're far away from both the Earth and the Moon. Could be. Could be. I'm not sure what it's called, but could very well be. Not sure. Not sure. Now, even when we look at that one, Travis, that point between the Earth and the Moon where the force of gravity is zero, even that's not quite true because Mars is out there. Mars is pulling in some other direction, but it's so far away, relative to the Earth and the Moon that, the force of gravity caused by Mars is going to be really, really, really small. So is there ever really a point where the force of gravity is zero? No, there isn't. But when we look at things that are close by, yeah, they can balance out and make the force caused by the two of them zero. But there's always other things, right? Things that are at the edge of the universe are still applying the force of gravity on us. It's just so small that we can't really measure. Here's a question. Notice we're on chapter 4 now, by the way, if you guys don't have that downloaded yet. 4.1 on page 206, it says Mount Logan in the Yukon is 6,000 meters basically above sea level. What are we in Calgary above sea level? About 1,000-ish, I think. About a kilometer or so above sea level. 6,000 meters is a lot higher, obviously. It's like climbing from Vancouver to Calgary 6 times, except you don't have to go the horizontal distance along with it. I heard earlier this year, there was a team, I forget which hockey team it was, they had a game against Calgary and they had a game against Edmonton all in the same week. And they had a break before that. They had like a 3 or 4 day break before that. Well, when they came to Alberta, they came right after their last game and wherever, somewhere on the East Coast, and they came to Alberta right away, right after that game. And they spent 3 days. I think they spent a day or two in Banff, and then they spent a couple days doing whatever in Alberta. Why would they come so early? Why is it like, why not just hang around at your house with your family for a couple days and then fly to Alberta and play your hockey games? Yeah, the altitude's a bit of a problem, right? Calgary and Edmonton are at a little bit of an advantage. Colorado, same thing, and a little bit of an advantage over some other teams because of the altitude. The air is thinner here because the acceleration due to gravity is slightly lower. It doesn't pull air down quite as much, right? There's not as much air here as there is in, say, New York or in Vancouver. The air is thinner. So for us, that's not a problem because we're used to it, right? Our bodies have adapted to that. But if you play hockey on the East Coast or on the West Coast, for that matter, all the time, then you haven't adapted to that. It takes you a couple of days to kind of get used to that. So if you get that opportunity to come and spend a couple of days to acclimatize yourself to that, and that's beneficial to you, obviously. Yep. Basically, yeah. Yep. It's like altitude training for athletes, right? Before the Olympics in Calgary in 1988, athletes came to Calgary weeks before the Olympics, or even months in some cases before the Olympics, to not just acclimatize to the altitude, but actually train at the altitude. There's some debate on the value of altitude training, though, because, I coach cross country, and I've thought about doing this before. Let's go to the mountains and let's train at a higher altitude because that's going to improve your endurance, right? So that when you go to a lower altitude, you're going to be so much better, right? The problem is this, and I think the jury is kind of still out on the value of that because the problem is this: you go to the mountains, high up in the mountains, you train at that higher altitude. Okay, that's great. Your body becomes more adapted to that. You go to the lower altitude, you're even better at the lower altitude where there's more oxygen. The problem is at the higher altitude, you can't train as hard, right? If you're in Vancouver, you can train harder than you can in Calgary because there's more air in Vancouver. If you could train just as hard in Calgary as you could in Vancouver, you'd be better off training in Calgary. But because you can't train quite as hard because there's not quite as much air, it might be kind of a wash, right? Yeah, no, that's right. But training there is the idea is to build the capacity, right? Yeah. So I don't know. I think the jury is still out on the value of that, but there's people on both sides of that, whether it's really valuable or not. Anyways, let's go back to this one here, okay? This is a place where you probably don't want to train, 6,000 meters above sea level. Not very much air at all up there. It's the highest peak in Canada. Earth's mass is 5.97 times 10 to the 24 kilograms. That's heavy. That's why the Earth isn't being pulled up like you're being pulled down. The radius is 6.38 times 10 to the 6. We say the equatorial radius because it actually does change a little bit depending upon where you are. It's not a perfect sphere. What would be the difference in the magnitude of the weight of a person? Weight, by the way, we know that weight is the force of gravity, right? The weight is the force of gravity acting on the person. What's the difference at the top of the mountain as compared to at its base, essentially compared to sea level? Well, okay, here's the mountain. Okay, the base of the mountain is 6.38 times 10 to the 6 meters from the center of the Earth. We got another 5,959 meters above that to the top of the mountain. Let's get the force of gravity at the top of the mountain. The force of gravity there is equal to Gm1 m2 over r squared. That's 6.67 times 10 to the minus 27 times the two masses. Mass number 1 is 55 kilograms, and mass number 2 is 5.97 times 10 to the 24. If you put those backwards, it doesn't make any difference. What's R going to be here? What do you think R is going to be for the force of gravity experienced by the guy at the top of Mount Logan? Yep. Sorry? 6.38 times 10 to the 6? No. Where did that come from? Rucker, where did that come from?
Putting the static extra meters.
Yes. Yeah. We need the distance from the center of the Earth to wherever this guy is. And that's 6.385959 times 10 to the 6 meters. We had to add those two distances together. Rucker, do you have the value for that now? Just wait 2 seconds, guys. Don't pack up yet. What's the value of that? 4.07 times 10 to the 13 newtons. I think that might be wrong. That's a big, that guy is heavy if he has a weight of 10 to the 13 newtons. Yeah, there's a problem right there. That shouldn't be 10 to the minus 27. That should be 10 to the minus 11, right? Yeah, that's better. Hayden, that's probably why you got the wrong number there.
No, I thought we were calculating for a number worth 5.
Okay. Guys, that's going to give you a force of gravity at the top of the mountain. We're going to also find the force of gravity at the bottom of the mountain. Those two numbers are going to be different. You're going to be heavier at the bottom of the mountain than you are at the top of the mountain. What are you going to do with those two numbers? Subtract them. That's going to give you the difference, right? The difference in the magnitude of the weight of the person. Remember, weight is force of gravity, and now we can find force of gravity without knowing what G is, without knowing 9.81 meters per second squared. Homework, practice problems on page 206. Have a good weekend, guys. We'll see you on Monday.